All right, friends, welcome to Physics, February 12th. Today is a special day for the Europeans because they would write this as 12 February 21. So if you write this as 12/02/2021, you can read that backwards. You can flip it upside down. You can flip it left to right, and it's always the same. Kind of cute. I'm asking us to celebrate it today because, those cute, nice, easy things to celebrate, why not? We can celebrate it again on December 12th of this year. Okay, what did we do last time? Last time, for physics, we applied Newton's second law to everyday forces. We talked about the gravitational force, which we can find by taking m times g. So for instance, if we have a mass of 1 kilogram, that would have a gravitational force of around 9.8 newtons. Remember, a newton is a kilogram times meters over seconds squared. And we also talked about the normal force. The normal force is the force that's pushing back up from a table when you rest a block on it. The force of gravity pulls the block down. The normal force pushes it up. And that block now is in equilibrium because the sum of those two forces, the vector sum, is 0 because you have all the forces up being counterbalanced by all the forces down, or vice versa. Then we also talked a little bit about tension forces in ropes, which can be a little tricky because they act in different directions on different objects. So here the tension, this is a block being pulled along by a rope. The tension is pulling to the right on the rope. It's pulling to the left on the hand. And we finally put these things together with a block on an inclined plane, a famous physics problem that is a little bit tricky because it requires us to split up our forces into two directions instead of just having our mg in. We can find out what this angle is because we have a similar triangles issue, and then we want to split up this gravitational force, this mg, into a component that is perpendicular to the surface, and that will be counteracted by the normal force of the surface pushing back on the block. And then we have a component that is essentially pulling the block down the ramp. So it's pulling in this direction, and that needs to be counteracted by a cord in a particular problem. But if we cut the cord, that is the force that pulls the block down the surface. And the fact that that is smaller than just mg by itself is why our acceleration for an object that's sliding down a slippery surface is nonetheless it's a smaller acceleration than just free fall acceleration falling straight down. Okay, it is Friday, and Friday means that we have a quiz today. So I hope that's not a surprise to you. You may have already taken the quiz by the time you watch this video. But here's an example of a type of problem you might see on a quiz this week. In fact, there is this problem on the quiz, except instead of F, M, and A, I have put numbers in there. And it says a net force of F is required to give a mass M an acceleration A. F equals M times A. Okay, so that's true in this case. If a net force of 6F is applied to this object, to an object with a mass of 2m, what is the acceleration on this object? Well, if 6f equals 6ma, then I would have to put a 3a right there to get my answer. And there we go. Okay, so on the problem on your quiz, you might have to, for instance, solve for an m in the middle of the problem, but it should be doable. Okay, here's another problem. During gym class, a boy climbs a vertical rope. All right, my artistic career is coming along nicely. And temporarily stops halfway between the floor and the ceiling above. Considering the following forces: gravity, normal force, friction, and tension at the moment, ignoring any effects due to surrounding air. Which of these forces are acting on the boy? All right, well, as is our wont, we're going to represent this boy in a sort of a dehumanizing way. We're just going to write a dot. What's one force? Well, that force of gravity, I'm going to put a check mark on that. Yes, force of gravity is acting on it. Normal force? Well, normal force, you usually have to be sitting on some surface, so I'm going to say he's not sitting on the floor, so there's no normal force. Friction? Well, it's kind of confusing because, after all, he would feel some sort of a rubbing on his hands. But in this case, I would say probably not. It would be better to attribute that force upward to the tension force. So you've got a force, gravity down, tension up. And just to be clear on this, let's say that he started sliding down at a constant rate. In that case, you might have friction going up and gravity going down, and tension also pulling up. In that particular case, if he's sliding down at a constant speed, the forces would also have to balance. So something to keep in mind, Newton's first law tells us that if you're going at a constant speed, you don't need to explain that. That's inertia. That's the natural state of objects. They like to either continue to move or continue to stay still. But you don't have to explain it if they're moving. In that, if you're not accelerating, your net force is zero. But in this case, he's not accelerating and he's not moving, and so we just would say gravity is zero, tension force is zero. And there we go. Okay, just for fun, by the way, I don't know if you remembered, but there is a quiz today. All right, it asks us, in which case will the magnitude of the normal force on the block be equal to mg times f sine of theta? So this is a normal force that's bigger than the usual case. So here's our usual case, which is just normal force pointing up and gravitational force pointing down. In that case, these forces are the same size and they're in opposite directions. However, in this case, we have case 1, case 2, and case 3. Now, of course, you can do some work and figure this out by writing down a three-body diagram. I want us to just draw the diagrams, though. Now, in this particular case, in case 1, you have your gravitational force acting on this block. You also have a force in this direction acting on the block. That's that F that's drawn in the picture. Now, if the block doesn't go through the ground, it doesn't start accelerating up and down, that means that the forces in your y direction have to be balanced. So your normal force has to be as big as the force of gravity in that x direction, plus this extra size of that force there. So it's also going to have to be, okay, so altogether, that's going to be the size of your normal force. Okay, so it's got to counteract this, and it has to counteract the component of that force that's also there. So there's your normal force. On the other hand, in this second case, you have the force of gravity pushing down, but your force is pulling up and to the right, okay? In this case, that force is pulling partially to the right and partially up. In this case, you don't need as much of a normal force to counteract the force of gravity going down. So there's the F, here's the force of gravity, there's the normal force. The normal force pushing up is now smaller than the force of gravity because part of the force pulling up and counteracting that force of gravity is already being applied by this pull on the block. And then in case 3, we have this force, and we have the gravitational force. And notice that the net force is then going, in the x direction, is then going to be the force in this direction minus the force of gravity that's in the same direction as that force. And the normal force now is also going to be smaller than it was in this usual case because only that component of the force of gravity that's in the direction or perpendicular to the direction of the plane has to be supported. Sorry, that's the normal force. So the upshot is that in case 2, the normal force is smaller. In case 3, the normal force is smaller. In case 1, the normal force is bigger. So that's the only case that we can even consider as being possibly correct. And of course, if you work out the math, you'll see that this extra component here is going to be F sine theta. And so the force of gravity plus F sine theta both need to be counteracted, and that gives you your normal force. Okay, enough words on that one. Oh no, I have another quiz question. Oh boy. Okay, in this one, this is also good because it's basically a homework problem that I gave you. In the homework problem, you have sausages hung on these strings, but nonetheless, it says 2 identical cylinders are attached to opposite ends of a spring scale via very light ropes, the masses of which can be neglected, that runs over frictionless pulleys as shown. When the same scale was suspended from the ceiling and one of the cylinders was hung from it, it indicated its weight is W newtons. What will the scale read in the configuration shown? All right, now, the forces on each one of these objects has to be balanced because each one is just sitting still. So they're not accelerating. That means the force has to be balanced. Notice also that would be true if they were simply moving at a constant speed, as might be the case in one of your quiz questions. Okay, so let me draw some free body diagrams for those 3 objects. The scale, the weight on the left, and the weight on the right. Now, it tells us when the same scale was suspended from the ceiling and one of the cylinders was hung from it, the scale indicated its weight is W newtons. So that means that the force of gravity here is pulling down with W newtons on either side. However, each one of those cylinders is not accelerating, so that means that the tension force pulling up, there's a tension force on this side and a tension force on this side, has to have the size of W. Well, okay, so what's happening here? Well, in this case, this scale is not accelerating. It's being pulled to the left by the rope on the left, and it's being pulled to the right by the rope on the right. And if the force here is T, the force there also has to be T. The force on this side has to be T. How big is T in each case? The size of T is simply equal to W newtons. Okay, so I mentioned this because this result is a little counterintuitive. I know for my case, when the scale is attached to the wall and you hang something on it, it's not especially surprising that the amount of force would just be the gravitational force on this cylinder. On the other hand, when you hang something over here and hang something over there, you want to feel that you're going to get 2 W newtons out of it. But that in fact is not the case. If I simply replace this by attaching it to the wall, I get the same tension force as if I balance it with 2 gravitational forces. So a little bit of a thinking question on that one. Okay, so that's enough old stuff. Today we are going to introduce one new idea, and that is Newton's third law. Okay, so Newton's third law is one that you probably heard in science class in high school, but I feel pretty confident that most people are not actually appreciating Newton's third law, because often you learn it, you hear it, you understand the words, but you don't understand the idea. So the idea, of course, is that if you have two bodies interact, the forces on the bodies from each other are always equal in magnitude, opposite in direction. So the example that they give in your book is that if you have a book C and a book B and a crate C, and they're leaning against each other, the book is providing a force on the crate is providing a force on the book. How are the sizes of the force related? They are equal. How are the directions of the forces related? They're in opposite directions. Equal and opposite. Okay, so everybody knows this slogan, but let's see if we understand the idea. Now, on your book, they give you a good example of paired forces. Now, the paired forces that they give you are, for instance, a cantaloupe on a table on planet Earth. And I guess this cantaloupe is the size of the, what is this? It's the size of the Atlantic Ocean. Okay, well, in any case, we can exaggerate a little. Okay, now, the thing to notice about these paired forces is that they're acting on different objects. So for instance, if you have the cantaloupe being pulled on gravitationally by the Earth is also being pulled on gravitationally by the cantaloupe. Now, the thing that's a little surprising in this is that the force that the cantaloupe is acting on the Earth with is the same as the force that the Earth is acting on the cantaloupe with. Okay? The only difference is that the Earth has an absolutely enormous mass and the cantaloupe has a much smaller mass. So when you drop the cantaloupe, you notice the cantaloupe accelerating. The Earth, in theory, is also accelerating slightly upward towards the cantaloupe, but the mass difference is so enormous that you don't notice the Earth accelerate. Now, there's another force pair in this, which is the cantaloupe is pushing down on the table. That's this. And the table is pushing up on the cantaloupe. That's this. Now, the thing to notice about this, as I write here, is that these are different objects. The cantaloupe and the Earth, they are exerting paired forces. The cantaloupe and the table are exerting paired forces on each other. The reason I stress that is that you can have forces that are equal and opposite without those being Newton's third law forces. So, for instance, the size of the force pushing up on the cantaloupe and the size of the force pulling down on the cantaloupe, those are the same size and they're in opposite directions. Both are, however, acting on the cantaloupe. Those aren't paired forces. It's not the cantaloupe acting on something and something acting back on the cantaloupe. Those two are both acting on the cantaloupe. So in this case, those are not Newton's third law paired forces. They just happen to be paired forces because the cantaloupe is in equilibrium and it's not accelerating. Okay, so that idea is a little bit hard to appreciate. I have put on your PowerPoint slides for today a video that I would like you to watch right now. So pause this video, go watch that video on YouTube, and we'll come back. Welcome back. Okay, I'm not going to repeat what he said on that video because I think he says it better than I could. But this video is great at highlighting the sorts of errors in thinking that people have surrounding Newton's third law. Now, here's another example that he doesn't use in that video, but that I think is very effective at revealing the sorts of problems that people have with Newton's third law. Now, Newton's third law says that each force is paired with an equal and opposite force. Okay, so far so good, nobody has any problem. Now, here's a case where a horse is pulling a cart. Okay, you have seen this happen in life and probably in movies, and you know that this horse can indeed pull it forward. However, you know that it happens in life, but does it work in theory? Okay, so here's the force of the horse on the cart. Here's the force of the cart on the horse. Now, if you've ever seen an astronaut movie, when two astronauts are on the International Space Station and they push off each other, this allows one astronaut to go one way and the other to go the other way. It's the same thing with a rocket launch. The rocket pushes stuff out of its butt and it goes forward because the particles in the rocket are being pushed this way, the rocket is being pushed the other way. So Newton's third law works very well in those types of cases because one object goes the one way, the other goes the other way. However, this is not that sort of case. The horse is going in the same direction as the cart, and yet it's being pulled backwards by the cart, according to Newton's third law. Oh boy. So at this point in class, I would ask people, what do you think are some reasons? And people invariably give wrong reasons. Now, I would like you to try to see if you can come up with a correct reason, or at least guess a reason. Unfortunately, I'm not interacting with you. This is just a video. And so I will simply tell you what I think is the resolution to this paradox. And what I think is the resolution to this paradox is that you have to include the ground. So, is it true that the horse and the cart are pulling on each other with the same amount of force in opposite directions? Yes. So the force of the horse on the cart and the force of the cart on the horse, those are balanced. If those were the only two forces that we could care about, and the horse and the cart or the wagon were connected, you indeed would not have any motion. However, what happens is that you also have a force on the horse from the ground because the horse is pushing off of the ground. So the force of the ground on the horse. And then there's a paired force there where the horse is pushing on the ground. Force of the horse on the ground. Now, what happens here is that you have a net force. If this force is bigger than that force, you have a F net on the horse, you have a F net on the cart, and you have a net force on the earth. However, So as you're going forward, the Earth is, in theory, rolling back a little bit. But of course, since the mass of the Earth is stupendously enormous compared to the mass of the horse, or the mass of the horse and cart together, you don't register the force of the Earth, or the Earth rolling underneath the horse and the cart the way that you register them, because of course F equals ma, so the amount of acceleration that you get, it depends on your mass. So if you have a littler mass, the same amount of force causes a bigger acceleration. The Earth has a truly stupendous mass compared to that of the horse, so it experiences virtually no acceleration. Okay, so that's a good problem to think about. I will leave you with it. Oh, ho! Gotcha. We have another quiz question. We have a cell phone sitting on a desk. Which one of the following is the reaction force to the cell phone's weight on the desk? Okay, so remember, we have to have different objects. There's the desk, there's the cell phone. Okay, the cell phone pushes down on the desk. The desk pushes up on the cell phone. Okay, so the gravitational force on the cell phone, there is a gravitational force on the cell phone going down. There's a gravitational force on the Earth going up, but that's not the thing that's keeping the cell phone standing still. Okay, the gravitational force on the table, there is a gravitational force on the table, but its paired force is the gravitational force of the table on the Earth. The normal force of the Earth on the table, there is a normal force of the Earth on the table, but it is paired by the force being pushed down on the Earth. The normal force of the cell phone on the table, that one is just an X, because the cell phone is not pushing up on the table, it's pushing down on the table. And the normal force of the table on the cell phone, that gets a check mark, because the cell phone is pushing down on the table is pushing up on the cell phone. There we go. All right, so that's similar to the cantaloupe problem that we had a couple slides back. Okay, on this particular homework that's due Monday, I did not put a lot of Newton's third law stuff because I wanted to be done with the material for this homework by Wednesday. So if you have any homework questions as you work on them tonight, please shoot me an email. I'll try to answer. But we do have homework due on Monday. Here's a problem. It says that you have a firefighter who slides, who weighs 712 newtons, slides down a vertical pole with an acceleration of 3 meters per second squared directed downward. So you have an acceleration that's going in this direction. What are the magnitude and direction of the vertical force on the firefighter from the pole? Okay, well, he has a force of gravity. The force from the pole has to be pushing up, because otherwise he would simply be accelerating downward at 9.8 meters per second squared. He's not. So there has to be some force up that's slowing his rate of acceleration, his acceleration. So in this case, we would say F net equals F pole minus Fg. And so we'd go M times A equals F pole, we don't know what that is, minus M times G. It says that he has a weight of 712 newtons. Remember, when we're near the Earth, our weight is simply the force of gravity on us. So we can find out by using F times 9.8 newtons per kilogram. If we have this as 712 newtons, we can find out what his mass is and put that in here. The acceleration is going to be downward, so the acceleration we put in there is going to be minus 3.00 meters per second squared. And so you know what you can find out what the mass is, use that in those. You know what A is, you know what G is. You're going to use 9.8 meters per second squared. Right there. I already have a minus sign in there, so don't double use your minus sign. You just get to use it once. And then you get to find out what the F of the pole is. So it should be some value that is smaller than 712, but directed upwards. Okay, now here's the Newton's third law part of it. They ask, what is the magnitude and direction of the vertical force on the pole from the firefighter? So the force of the pole is acting on the firefighter pushing up. If you have Newton's third law, that means that the force of the firefighter has to be pushing down on the pole, and the magnitude of that push is going to be equal to the magnitude of the force upward from the pole. Okay? Now again, why is it that the pole doesn't start accelerating? Well, it's because it's attached to the Earth, and the Earth is basically soaking up a lot of our forces. And so a lot of your paired forces you never notice because they're being essentially redirected to the enormous mass that is that of the Earth. Okay, so that's our video for today. What are our big ideas? One is Newton's third law. For every force, we've got another paired force that's equal in magnitude, opposite in direction. Just because you have two forces that have the same size and are in opposite direction, that doesn't make them a Newton's third law pair. Remember, our normal force and our gravitational force on the same object are not a Newton's third law pair. It's two objects that are both pushing or pulling on each other. And as we saw with the horse and cart example, the mass of the Earth is important. And if you leave it out of these a lot of problems, you don't understand really how Newton's third law is playing out in the interactions that happen all around us. Okay, so good luck. Remember, today we have a quiz, and today we also have a homework. All right, so good luck, and have a nice weekend.